Alright, reaction number 3. So this is a combustion reaction. A combustion reaction is a hydrocarbon reacting with oxygen to produce carbon dioxide and water. So hydrocarbon is just a molecule made up of hydrogen and carbon. So the identity of the hydrocarbon can change. But I'm going to use this one for this example. And it's always going to react with with oxygen. And it's always going to produce carbon dioxide and water. So the only thing that ever changes between combustion reactions is the identity of the hydrocarbon. So basically how many carbons and hydrogens it has, and then as a result of that, the coefficients will change to make sure that it's balanced. Right. So now here, looking at the oxidation numbers. Hydrogen, here in this hydrocarbon, is bonded to a non-metal. So according to our rules, that has to be +1. This one's a little trickier. See if you can try to figure it out. Pause the video now if you want. But this is definitely a trickier oxidation number. It actually ends up being -8/3. This is really the only kind of reaction where you most likely will see a fractional oxidation number. They're not very common, so if you didn't get that, don't feel too bad. You won't see that very much. Here we have the elemental state of oxygen, so it's 0. Alright, CO2. Oxygen is now in a compound, and that's not one of our exceptions, because remember, X2O2 is what you look for, not, so if this was C2O2, that could be a peroxide, but that's not what we have here, just CO2. That's not one of our exceptions for oxygen, so we're going to have -2. And there's 2 of them, so that's -4. So to make this balance out, carbon needs to be +4. Here, this is also not one of the exceptions, so oxygen is -2, and hydrogen is bonded to a non-metal, so hydrogen is +1. So hydrogen does not change. It's +1 in both ways, but carbon goes from -8/3 to +4. So that means that carbon is going up in oxidation number, so that's oxidizing, which means that this entire molecule, C3H8, is your reducing agent because it contains the atom type being oxidized. Oxygen goes from 0 to -2, so oxygen is reducing. Right. Reaction number 4. This is a displacement reaction. And there's single and double displacement reactions, but in single displacement reactions, it's much easier to see redox process happening. That's what I'm going to show here, because you'll pretty much always be getting a redox procedure happening in a single displacement. So let's say we have solid zinc reacting with aqueous hydrochloric acid. That's going to produce, I'm sorry, let's see, should be 2 here. It's going to get zinc chloride plus H2 gas. Alright. Solid monatomic zinc, it's a metal, that's its elemental state, oxidation number of 0. Here, hydrogen is bonded to a non-metal, so it's +1, which means to make this equals 0, chlorine has to be -1. Over here, so chlorine is going to be so -1 again. So halogens like to be -1. There's unless it's fluorine, halogens can be many other things, but basically, if you have a halogen and it's not in any situation where it's forbidden by any of the 8 rules I gave you, then the halogen will likely be -1, right? So like for instance up here, chlorine couldn't be -1 because it was forbidden by both the group 1 metal rule and the oxygen rule, right? But here it's not forbidden by any of the rules, so we can make that -1, And there's 2 of them, which means that zinc has to be plus 2 to cancel that out. And this is the elemental state of hydrogen, so that's going to be 0. So zinc goes from 0 to plus 2. That's going up in oxidation number, so that's oxidizing. Chlorine does not change, but hydrogen goes from plus 1 to 0. That's going down. The hydrogen is reducing. So again, that means your HCl is your oxidizing agent. Alright, and the last equation type is a disproportion reaction. And that's actually when you have the same species simultaneously oxidizing and reducing. Now, it's not the same atom, and that's why I used the term atom up here, because it's not the exact same atom, obviously, both oxidizing and reducing. That doesn't make sense. But it's the same elemental species. So, for instance, let's look at this reaction here. So, starting with the reactant side, Cl2, I forgot to write that. So hold on, that's gas. So that is the natural elemental state of chlorine. So that's 0. Here, hydrogen is bonded to a nonmetal, so it's plus 1. And oxygen is going to be minus 2. And that minus 2 plus 1, that is minus 1, so it actually makes sense that it adds up to the charge. Here, oxygen has to be minus 2, and this whole thing has to add up to minus 1, which means that chlorine here is going to be plus 1. This is a monatomic ion, so that that oxidation number is just going to be the same as the charge, so that's minus 1. Here for water, oxygen is minus 2, and hydrogen is plus 1 like we've seen before. So if you look, oxygen is minus 2 everywhere, and hydrogen is plus 1 everywhere. Neither of those change. However, chlorine starts as diatomic chlorine, and so both of those chlorine atoms have an oxidation number of 0. One of them turns into this molecule where it goes to plus 1 and it oxidizes. The other one goes here as its own ion where it goes down to minus 1, thus reducing. And that is a disproportion reaction.